So bago po tayo magsimula, I would like to share some house rules in order to facilitate a smooth session for everyone. For our Zoom participants, we would appreciate it if you could turn your audio and video cameras off during the webinar. If you have questions or comments, feel free to type them on our Zoom chat box or YouTube live comments, and we will try to accommodate as much questions and comments as possible. After the talk, we will have a 30-minute Q&A where the Zoom participants will have the opportunity to ask their questions live. We would also like to request for everyone to not record the webinar. The full video of the session will be posted on our official YouTube channel. For those who would like to receive a certificate of participation, a Google form link will be posted on our Zoom chat box, YouTube live comments, and YouTube video description towards the end of the webinar. Please make sure that you enter the correct information, especially your email address, to ensure receipt of the certificate. Also, for you to obtain the certificate, you will need to subscribe to our YouTube channel as well as follow our page on Facebook. Please note that we receive hundreds of requests and it takes around 7 days or so to process all the certificates. If you do not receive your certificate after a week, please feel free to send us a message on Facebook or email us at philscihub@gmail.com. So again, welcome po sa Philsci Hub. Welcome to all our Zoom participants and our YouTube live viewers. For those who are new and may not be familiar with who we are and what we do, allow me to share our mission and vision in the next few minutes. Filipino Science Hub is an online platform founded by our CEO, Filipino scientist Dr. Jeffrey Camacho Bunkin, back in 2012. Currently, we are a registered nonprofit organization based in Houston, Texas, United States. Our mission is to promote STEM education and the culture of research among students and teachers in the Philippines and abroad. Our current global leadership team is comprised of volunteer Filipino scientists and seasoned STEM educators from different parts of the world. Our vision is to see a technology and innovation-driven Philippines, and we believe that this can be achieved by creating a new generation of well-rounded Filipino STEM enthusiasts. This vision is being carried out via our two major programs, the Philsci Hub Ed program and Philsci Hub Research University. Through Philsci Hub Ed, we are able to empower and support our teachers when it comes to strengthening STEM fundamentals education. We believe that this is important because the more equipped our STEM educators are, the more they can inspire our students to pursue a career in science, technology, engineering, and mathematics. Through this program, we have been able to serve our teachers by creating STEM teaching modules as well as conducting teachers training webinars, all of which are accessible on our website for free. So we have also been able to collaborate with major educational organizations that have the same goals and advocacies as Filipino Science Hub. Through these partnerships, we have been able to further expand our reach and help more students and teachers, especially during the time of pandemic. So together, everybody achieves more. The other major program that drives our vision forward is Philsci Hub Research University. We believe that in order to strengthen a STEM culture, students also need to be able to learn how to conduct a scientific research. As we know, many scientific and technological breakthroughs happen through research, and we would like to equip our younger generation by providing them proper scientific research training. So ika nga po, start them young. Here at Philsci Hub Research University, we provide free courses on fundamentals of scientific research, such as research ideation, literature review, how to write a research proposal, how to communicate your research work to the scientific community, among other courses. Through this program, we are also able to bring practicing scientists closer to the STEM educational sector. So because of this closer contact, our students become more aware of the possible STEM career paths available for them and how these careers contribute to the advancement of the society around them. So up to date, we have been able to reach over 70,000 students and teachers all over the world, and we know that this will continue to grow in the years to come. And this is why we are all very excited on what is in store here at PhilSci-Hub. Our official website is www.philscihub.com. This is where you can access all our materials such as webinars, tutorials, modules, virtual lab, and special features. We are also present in several social media platforms such as Facebook, LinkedIn, YouTube, and TikTok. So follow us wherever you're most active on to get updated with our web events. So again, thank you for being with us this morning. And to officially start our webinar, I would like to turn the virtual floor over to our host for today.
Okay. Good morning to everyone. So magandang umaga sa ating mga participants dito sa Pilipinas and to those who are joining us from other parts of the world. Good afternoon or good evening to all of you. So I'm Karen Lacerna, a member of the PhilSci-Hub family and also the equipment specialist for the chromatography laboratory of De La Salle University Central Instrumentation Facility. So we are in our third webinar of the DLSU CIF and PhilSci-Hub webinar series on modern analytical methods. So today we will be hearing from Dr. Virgilio Ebajo Jr. on NMR Spectroscopy for natural products research. But before we start with Vir's talk, we have here Dr. Drexel Camacho, Scientific Director of De La Salle University Central Instrumentation Facility, to provide an overview of the research and analytical capabilities of CIF and to talk about our partnership with PhilSci-Hub in this webinar series. So now, good morning, Sir Drexel.
Hello, good morning, everyone. Can I share my screen? I cannot share my screen.
Okay, sir. Pwede na pa.
Okay. So, good morning, everyone. My name is Drexel Camacho from De La Salle University Central Instrumentation Facility. And we welcome you to this webinar. And De La Salle Central Instrumentation Facility is a repository of advanced instrument from De La Salle University, and we cater not only to De La Salle University, but also to all researchers all over the country. We are located in DLSU Laguna campus in Binyan, Laguna. So what we do is we manage and serve the research needs of researchers from all over the country, and we use we have available instruments that are for use for any researchers. We have the NMR laboratory where the nuclear magnetic resonance is, and which is our topic for today. So listen carefully to Dr. Ebajo as he gives an overview of the nuclear magnetic resonance and what it can do, and maybe you can plan out your research activities through this instrument. And I guess last September, Mr. Christian Ryan Argamino talked about molecular spectroscopy, and the instruments related to that are located in this spectroscopy laboratory, where we do have the UV-Vis, the FTIR, particle size, the ICP-MS, and the elemental analyzer. And on January, Dr. Karen Lacerna will talk about chromatography, where instruments like the QTOF LCMS, the AHPLC, preparative LC, and GCMS can be introduced to you. And last October, I guess, Dr. Jose Esmiria Jr. talked about electron microscopy, where our center handles the transmission electron microscope, the scanning electron microscope, and the focus ion beam. And I guess by December, Mr. Michael Arnante will talk about the confocal laser scanning microscope and what it can do. And we also have what we call the wind tunnel testing laboratory, where we have an instrument that allows us to model our wind in different applications. So what we do is we serve the research needs of the country by accepting samples for analysis. And we can also, if you need help in processing your samples, we also have our laboratory, common laboratory instrumentations. And we also offer training for training needs for fundamentals as well as hands-on use of the instruments. We also serve you through consultations of your research designs and how to prepare the samples, and of course, what analyses are necessary. And of course, in terms of the analysis, it depends on your research objectives. So we would like to ask you to consult with us first before sending your samples, because to help you better, then we should be able to analyze and understand your objectives. And of course, we offer collaborations for research, and also we serve the researchers of the country through training and like this participation with the PhilSci Hub. And we're very happy with our participation with PhilSci Hub as we reach more people, more students through the training that we conduct through this PhilSci Hub regular session. And we would like to continue with this one, and this partnership allows us to reach more students, which is in line with our objective to create a research culture among Filipinos. And we are here to serve your research needs. Please contact us at DLSU at cif@dlsu.edu.ph. If you have some questions, please post your questions later. Dr. Karen Lacerna is part of CIF, as well as Dr. Virgilio Ebajo. Good day, everyone.
Okay, thank you very much, Sir Drex, for the introduction to CIF. And again, as mentioned by Sir Drex, if you have any questions or inquiries, please do let us know through cif@dlsu.edu.ph, or you can also post your questions later, and Dr. Veer and I will try to answer them. So, okay, let's move to our talk for today. So, for today's presentation, we have Dr. Virgilio Ebajo Jr. He is our equipment specialist for the NMR laboratory at DLSU CIF, and he earned his PhD in chemistry from De La Salle University. So his research interests include organic synthesis, green chemistry, carbocatalysis, and the development of novel organic reactions. He has published 28 research papers. So sakalam to si Veer, he on topics related to natural products isolation and synthesis of small compounds. So again, he is managing our he is taking care of the NMR, our 600 megahertz NMR, which can perform analysis for both liquid and solid samples. And we offer service analysis, research collaborations, and he also conducts workshops and trainings on NMR principles and hands-on operations. So everyone, to discuss NMR spectroscopy for natural products research, let us welcome Dr. Virgilio Ebajo Jr.
Thank you very much, Karen, for that introduction. Let me now share my screen. Okay. So, good morning. I hope my slides are now visible. So today I'm going to talk about the application of nuclear magnetic resonance spectroscopy for natural products research. Now, the way I designed the talk today is it's like a tutorial type, wherein you can, if you are starting on your natural products research and you are not familiar with how you can determine the structure of your isolates, then this talk will definitely help you. So if you are not in the field of chemistry, like if you are in biology or pharmacy and you are interested in doing natural products and isolating compounds, then this will be very useful. So to start, natural products are compounds coming from natural sources. Now in Philippines, most of the natural products research deals with samples such as plants, terrestrial plants, fungal samples, and marine plants or corals and sponges. Now, there are several drugs that have been isolated from natural sources that were successfully commercialized. And one of the most famous one is the paclitaxel. So paclitaxel, this molecule here, is an anti-cancer compound, and it was isolated from these three, the Pacific U3. So during the isolation study of paclitaxel, 1,200 kilograms of tree bark can produce 10 grams of pure paclitaxel. So paclitaxel is very successful because it was commercialized as an anti-cancer drug for different types of cancer. So kung pumunta kayo sa pharmacy today, you can see the brand name Taxol, and that actually contains paclitaxel as the active component. So why is natural products research important in Philippines? So Philippines is one of the 17 mega diverse countries in the world. So meaning sobrang taas ng biodiversity sa Philippines, and there is a large number of animals, plants that can only be found in the Philippines. So sobrang daming endemic na plants sa Pilipinas. And what we can do is we can study those kasi hindi naman na sila makita in other parts of the world. So nasa atin lang siya. So if we try to collect them all and then study them, maybe we can find another paclitaxel or another compound that can cure current diseases that we are facing right now. So a typical natural products research. So sa natural products, you start with the identification of your plant sample. So maybe you want to determine the compounds present in a plant that shows a very good biological activity. Halimbawa, meron siyang ability to fight dengue, for example, and you want to know which compound in that plant contributes to that biological activity. So you choose the plant. And then once you selected the plant, you perform solvent extraction. So you use different types of solvent depending on the polarity that you are targeting. So most of the time, use methanol, ethanol, and chloroform as the extracting solvent. But there are also some researches which deals with water-soluble extracts, lalo na yung mga nagtetest ng different types of teas because tea is usually prepared using water. So they are extracting it with water. Now, once you have your extract, this is considered as a crude extract. So sobrang dami niyang components dyan. You will now perform fractionation and purification using different types of chromatographic techniques. So you can use either gravity column chromatography, you can use preparative column, you can use Cepatex. So it depends on your laboratory's protocol. So if you look at journals, mapapansin nyo na bawat laboratory, meron silang kanya-kanyang fractionation protocol. And if you are still starting on your natural products research, I suggest that you follow some of the extraction protocols that are present doon sa mga journals that you are consulting. So once you perform the fractionation and purification, you will get your natural products isolate. So it can be in a form of a liquid or it can be in a form of a solid, which hopefully a crystal. Now, most of the time, natural products researches in Philippines ends on this part, dito sa solvent extraction. But maybe because they are not really aware with the fractionation methods, or they are not aware on how to determine the structure of isolate if they will get one. So kaya kapag umattend tayo ng mga local congress, for example, you will notice na most of the researches are just ending modern instrument. So before we need to do this
So Hi, Karen. Mukhang may connectivity issue si Sir Veer.
Hello. Okay. Sorry.
Ayan, sir. Okay na po. Okay na po. Para yung yung dalawa pong slides nyo parang naka-cut off, sir. Yun po.
Okay, sige. Okay.
All right. Thank you.
Okay. So, to continue, before the advent of instrumental methods for determining the structure of compounds, ito yung mga ginagawa to determine the structure of your isolates. So first, we need to prove that the sample is homogeneous. And to do that, we usually perform multiple recrystallization methods, and we test the melting point of the sample. And dapat constant yung melting point ng crystals na makuha ninyo. And aside from that, we perform combustion analysis to get the empirical formula. And we also determine the molecular formula using different techniques such as vapor density or cryoscopy. And also, we need to test the functional groups present on the compound using different qualitative tests. Now, after you get all of these properties, you will then go to a compendium. So for example, this is the Beilstein compendium for organic compounds. And then you will look for a compound which has the same properties as the one that you have isolated. So for example, you can look at the melting point, and if you've noticed that you get a compound with a melting point of 187 and a molecular formula of C9H16O, then you probably have isopropyl cyclohexanone. Now, what if you get a compound that has a melting point of, let's say, 188? So medyo malapit siya dito sa 187 and medyo malapit din siya dito sa next compound, which is isopropyl cyclohexanone 4. So dito ka na magkakaroon ng problema kasi you are not sure which of these two compounds you have right now. Now, also another problem that you will get is what if wala yung compound mo dito sa compendium. So ibig sabihin yung compound mo is new and it was not isolated before. So kailangan mo i-prove yung structure niya. So to do that, you need to perform degradation reactions by cleavage at the functional groups. So for this, you need to perform a set of organic reactions such as ozonolysis, reaction with various reagents, tolerance tests, etc., in order to prove the structure and the presence of different functional groups in your compound. So this is not an easy task, and this usually requires pure sample in grams scale. So hindi pwede yung micrograms lang, usually dapat mga nasa 50 grams. And this is a very big problem kasi in natural products, we cannot really get isolates in the grams scale. Most of the time, we are in milligrams. So masyadong tedious yung natural products research noon. So fortunately, we now have different instrumental techniques that can help us in determining the structure of the compounds. So some of these are the infrared spectroscopy, which can help you identify the functional groups present. And if the compound is present in the library, then you can use the fingerprint matching to determine the structure of the compound. You can also use UV spectroscopy.
Alright. So, hintayin lang muna po natin ulit si Sir Veer kasi mukhang ano po,
determine the structure of the compound. Okay. And if you have a high resolution map,
so sa atin pong audience, so ano pa, ayan, nakabalik na si Sir Veer. Sir, welcome back.
okay, I'm very sorry, meron problem internet provider now.
Yeah, no worries,
Okay,
sir. No worries, sir. It happens. It always happens. So,
okay.
yeah, please proceed po. Thank you.
Okay, so to continue, you can use mass spectrometry to determine the structure by comparing the fragmentation
Done.
Yan. Hi, dear.
Hi, sir. Ayan. Okay, we're back.
Okay.
Right.
Okay. Sorry. Third world country problems.
No problem,
Okay.
sir. It's okay.
Okay. Okay. So also aside from those stated, the most important one is the NMR spectroscopy, which you can use to identify your compound if it's known by spectral matching. And you can also build the structure of novel compounds using all the information present, such as type of bonds, functional groups, and stereochemistry. And also, another important thing with NMR spectroscopy is that it can differentiate isomers, which is a big problem for mass spectrometry. Now, with the advent of modern instrumental techniques, that means that the natural products extraction protocol now includes instrumental analysis at the end, and usually it is NMR analysis. So once you perform NMR analysis and you interpret your spectra, you can get the structure of your compound, which can speed up the commercialization process for your isolate. So now I will go through the basics of NMR spectroscopy. So this is a very simple one, and I will try my best not to include any physics or quantum mechanics for this discussion. So in NMR spectroscopy, we have N as nuclear because we are dealing with nuclei of atoms. So let's first look into this tiny bar magnet model. So if you have very, very tiny bar magnets without any external magnetic field, they will be ordered in a random manner, such as this one. So your North Pole and South Pole nila are directed in a very random manner. But if you introduce an external magnetic field, then they will orient themselves either parallel or anti-parallel with the direction of the external magnetic field. So in nuclear magnetic resonance spectroscopy, we are dealing with nuclei, which has spins. So without field, they are also in random manner. But if you introduce an external magnetic field, then they can be either parallel or anti-parallel to that of the magnetic field. Now, since you have two different energy spin states, the one that is parallel and anti-parallel, then you have two different energy states. So in ground state, this is the direction or orientation of the spin that is parallel to that of the magnetic field. So they are in lower energy. And those spins that are opposing the direction of the external magnetic field are anti-parallel, and they have higher energy. So in NMR spectroscopy, we introduce EMR in the form of radio frequency in order to excite the spins so they can flip to the higher energy spin states. So after introducing the radio frequency, you will now get an excited state wherein you have an excess population on the higher energy spin states. Right. Now, the energy difference between spin states depends on the strength of the applied magnetic field. So meaning the stronger is the external magnet, the higher is the energy difference, the higher the population difference will be. And in NMR spectroscopy, we want this to happen kasi pag mas marami yung excess spin states mo, therefore mas marami yung spins that will generate signal. Okay. So also in NMR spectroscopy, we are dealing with also in NMR spectroscopy, right? So once the sample is on the excited state after the application of a radio frequency pulse, we will wait for the sample to relax in order to reach again the ground state. And this is where signals are detected during the relaxation, right? Right. So in NMR spectroscopy, we are dealing with the NMR instrument. So the NMR instrument is actually a system or a group of instruments, and it includes the superconducting magnet, the computer, and the spectrometer. So typically, if you look for NMR in Google, you will only see this one, the superconducting magnet. And however, in reality, hindi lang yung superconducting magnet yung makikita nyo sa laboratory. You will have these spectrometers, which are also very important. You will have the probe, you have the computer, and you will have the air compressor system. So the superconducting magnet generates the external magnetic field. And the reason why it's called superconducting is because it only acts as a magnet, as a very strong magnet under very low temperature. So that's on near the liquid helium temperature. So the superconducting magnet contains two different types of cryogen in order to maintain superconductivity. So we have the nitrogen and the helium cryogens. So in a basic NMR experiment, your sample is present on inside an NMR tube. So once your sample is in this NMR tube, wala pang external magnetic field. So the spin states in your sample is oriented in a random fashion. Now, in NMR experiment, you introduce your sample to the superconducting magnet dito sa top, and then your sample will be transferred to the probe on top of the probe dito. So once your sample is inside the magnet, the spin states on your sample will now be oriented either parallel or anti-parallel to the external magnetic field. So your sample will be floating on top of the probe or on the probe, and then the probe will introduce a radio frequency pulse in order to excite some of the spins on your ground state level, on the lower energy level, to the higher energy level, and then you will get the excited state. And then after that, the NMR instrument will wait for the sample to relax, and then signal will be gathered during relaxation. Okay. So what nuclei can be analyzed in NMR? So the most common is proton, the H1, and also carbon-13. But in theory, all of the nuclei that have a spin quantum number that is not equal to 0 can be analyzed in NMR. However, some of the nuclei have very low natural abundance or very low sensitivity, kaya hindi sila useful in NMR studies. But for natural products research, the most important ones are the hydrogen one, or the proton, and the carbon-13 nuclei. Because in natural products and in organic compound, ito yung pinaka-common na nuclei present. So in summary, NMR is like just like a radio, because we can tune into a specific radio channel or a specific nuclei in order to gather information about its surrounding. So ganun lang kasimple yung NMR spectroscopy. Okay, so NMR, in NMR spectroscopy, what you will get as a data is an NMR spectra. And the most common NMR experiment involves proton. So in order to be familiar with the NMR spectra, we will start first with this one, the proton NMR spectrum. So a proton NMR spectrum looks like this. So you have the y-axis as intensity, and then you have the x-axis as chemical shift in ppm. And do not be confused with the ppm scale of the NMR spectrum, kasi yung 0 is on the right side. And as you go to left side of the x-axis, mas tumataas yung value ng chemical shift in ppm. Okay? And in NMR spectra, we also have the term upfield and downfield, or shielded and deshielded. So the upfield region is on the rightmost side of the spectrum, and then the downfield region is on the leftmost side of the spectrum. Also in an NMR spectra, you will see signals, ito yun, which represents the types of nuclei that you are detecting, in this case protons. And then most of the time, we also have a reference. So in this case, this is a tetramethylsilane. And however, at present, we do not use TMS anymore, but what we use is a residual signal coming from the deuterated solvent. So what are the basic information that we can gather from a proton NMR spectra? So these are the four basic ones. First, number of signals, and it indicates the number of different types of hydrogen in the molecule. We can also use chemical shift in order to determine the type of hydrogens the molecule contains. So the chemical shift also refers to the position of the signal in the NMR spectrum, and it is in a ppm scale. So integration, or the peak area, indicates the relative amount or how many of each kind of hydrogen is in the molecule. And multiplicity provides additional information on the neighboring environment for various hydrogen in a molecule. Okay, so number of signals. Now, for example, we have this compound as a sample and we run a proton NMR spectrum. We know that acetic acid contains two different types of proton. One is on the methyl group of this portion, and also the acidic proton of the carboxylic group. So if you run a proton NMR spectrum of this compound, what you will get are two signals coming from this sample. So ito yon and ito. So this means that you have two different types of proton or hydrogen in your sample. So this signal is not part of the molecule, but this is a signal coming from the solvent. Right? So next is the chemical shift. So the chemical shift is the location of the signal in the spectrum in ppm. So for example, you notice a signal at a region of, let's say, 1.3 ppm. So that means that signal is probably due to a proton attached to a carbon, that is aliphat. Now, if you have a signal on, let's say, 10 ppm, then most likely that signal is coming from a proton of an aldehyde. So that's how we interpret an NMR spectrum. So the chemical shift correlation table for proton NMR is not really useful if you are already on the range wherein there are so many overlapping signals. For example, dito. So if you have a 5.1 ppm signal, hindi mo alam kung galing siya sa OH na to or galing siya sa aromatic ring. Hindi mo rin alam kung galing siya dito sa NH2 or galing siya dito sa olefinic proton na to. So that means that if you are trying to interpret an NMR spectra, dapat talaga magpa-practice ka because this is a skill that you acquire through practice. Okay. Next, for example, in this compound acetic acid, we have two different types of proton. You'll notice that one of the signal is on the lower ppm scale. It's on this side of the spectrum. It's around 2.2, I guess. And then one is on the 11 ppm. So if we go back to the correlation table, we know that the shielded signal at around this region to 11 is from a carboxylic acid proton. So ito yun. And then a signal that is on the deshielded region is probably coming from an hydrogen attached to a carbon or a CH3, for example. So ito yun. So with just the chemical shift and the number of signals, you can actually build the structure of a small compound. So another information that we can get from a proton NMR spectra is integration. So the integration will tell you how many of that proton is present on each peak by looking at the integral values relative to other signals. So for example, if we have this molecule again, the acetic acid, so this signal has an integral value of, let's say, 18 millimeter, that is the integral height. And then this one has an integral height of 6 millimeter. So if you will take the ratio of these two integral heights, you will notice that this is in a ratio of 1:3. So meaning for every one proton for this signal, you have 3 protons for this signal. And that is true for the acetic acid kasi you have 1 proton coming from the carboxylic part and 3 protons coming from the methyl part of the acetic acid. Now, This is very useful if you are dealing with a larger molecule, for example, this one. Kasi with just the integration, the chemical shift and the number of signal, you can easily build the molecule. Kasi if you look at the integral of this proton versus this one, you know that they are in a 1:1 ratio. So meaning, kung gaano karami yung protons na nag-contribute sa signal na to, ganun karami din dapat yung protons na nag-contribute dito. And that is true for this molecule because this proton is DCH2 and this proton is DCH2. So they are in a 1:1 ratio. So dalawang proton dito, dalawang proton din dito. So for aromatic ring, mas mataas yung integration niya kasi mas marami yung proton nung aromatic ring. There are 5 protons here. Okay. So next is multiplicity. So multiplicity is a phenomenon wherein a signal in a proton NMR spectrum is splitted into multiple signals. So for example, you will notice that sometimes you will get just a single signal for that type of proton. Sometimes you will get 2 signals of the same height or 3 signals of this height ratio. So this is actually due to the number of hydrogens that are present as a neighbor noong signal that you are looking at. So if the signal giving that, or if the proton giving that signal do not have any neighboring hydrogen, for example, this one, wala siyang neighbor kasi the hydrogen, the carbon attached to that hydrogen is attached to a carbon without any hydrogen, puro carbon to. So wala siyang neighbor. So meaning, walang magkukouple sa kanya. So no proton will split that signal. So it will get a singlet. Now, what happens if one of these carbon is now a hydrogen? So meaning the hydrogen in blue now has one neighboring hydrogen in red. So the signal of the hydrogen in blue will be split into 2. So because you have one proton coupled to that proton. So paano natin magagamit yung information coming from this multiplicity? So for this one, we follow the n plus 1 rule, where n is the number of neighboring hydrogen. So if you have n numbers of neighboring hydrogen, the signal of the hydrogen that you are looking at will be splitted into n plus 1 signals. So if you have n is equal to 0, the signal will be splitted into 0. So meaning the signal n plus 1 is equal to 1, so the signal will just be a singlet. If you have n is equal to 1, then n plus 1 is 2, so the signal will be equal to 2. So if you look at the multiplicity, malalaman mo kung ilan yung katabing hydrogen. So for example, this proton, the signal is triplet, there are 3 signals. So alam mo na ang katabi niyang hydrogen ay 2. Okay, so ganun siya tinitignan. Now, the signals for multiplets are also splitted with a specific J value in Hertz that you can compute in your NMR spectrum. And this gives you an information kung ano yung relationship ng dalawang protons na neighboring. So for example, if your J value is in 6 to 8 Hertz, that means the 2 protons next to one another are attached to carbons that are aliphatic or they are freely rotating. Now, if the J values is around 11 to 18 Hertz, that means the protons are attached to a carbon via double bond, and the other proton splitting it is trans to that proton. Now, if the coupling constant or the J value is at 6 to 15 Hertz, then it is vinylic and cis. And if it's 0 to 15, then it's vinylic and geminal. So if you know the J value of the, for example, doublet that you have, then malaman mo agad kung ano yung orientation nila. Okay? So you can extend this n plus 1 rule into quartet, quintet, sextuplet, septuplet. So if you have a quintet, that means you have 4 neighboring hydrogens, and the signal will be split into 5 different peaks. Okay? So if you have 5 neighboring hydrogen, it will be split into 6 peaks. So let's look at these compounds, for example. If you look at the CH3, and the signal generated in the spectrum due to this one is this green signal here. If you look at the structure, wala siyang katabing proton. The atom next to it is an oxygen, which do not have any proton. So dapat, following the n+1 rule, singlet ang signal na may kita mo sa kanya, and this is true. This is singlet. You can also observe this phenomena dito sa proton na to at 3.37. Ito yun. So wala siyang neighboring protons, so it's a singlet. But if you look at these 5 protons here that are not really equivalent, you will notice that they are split into multiple signals kasi ini-split nila yung isa't isa. Now, let's look at this more complicated structure. So, take a look at this signal in red for this proton. So, if you look at the structure, meron siyang isang neighboring proton, which is in green. And since it only has one neighboring proton, it will be splitted into a doublet following n+1 rule. So, you will notice that the signal contains 2 peaks. So, this is true for this green proton kasi ang katabi niya are oxygens, which do not have any protons. And katabi niya pa isa is carbon, which has 1 proton. So it should be splitted into 2 following the n+1 rule. So doublet kinikita niyo dito. And you can further investigate other parts of the spectrum, such as this one. So this CH2 here, this brown, ang neighbor niya is a CH3, which contains 3 protons. So following n+1, you will get 4 signals. And this is a quartet. So how do you interpret a proton NMR for an unknown natural product isolate? So first you start with the by listing all the chemical shifts of all the non-equivalent signals. And after that, you determine the type of protons by checking the chemical shift correlation table. And then you identify the type of proton by referring to chemical shift correlation tables. And then after that, you summarize all the information that you get into a table. So for example, you have this NMR spectrum. Ito. This is an unknown. And this is what you will usually get if you send your sample for NMR analysis. So wala siyang kasamang structure. Kayo yung bahala mag-interpret. So what you do is you list all of the signals in a table, such as this one. So you have a signal at 12.48, 9.4, 7.71, 7.55, etc. And then after that, you determine the multiplicity. You check if it's a singlet, such as this one, or if it is a doublet, such as this 7.71. And then you check the integration. So the integral values are on this part of the spectrum. And this varies depending on the brand of the software that you're using to process your NMR spectra. So for our case, the integral values are at the bottom, right? So this signal here has an integral value of 1, so it's for 1 proton. The signal here has an integral value of 2.53, so it's meaning the ratio is 2.53:1, etc. Now, after getting the chemical shift and the integration and the multiplicity, you go to the correlation table to check the possible proton type for that signal. So for example, for the signal at 7.71, then it falls on the region of the aromatic proton. So you say, oh, probably it's an aromatic proton. Same is true for 7.55, etc. So magkakaroon ka ng idea what most likely functionalities are present on your sample. Okay, so in natural products, sometimes or most of the times, it's not enough to just have the proton NMR in order to determine the structure of your compound. And if you have a very complicated structure, you need to run other NMR experiments, such as carbon-13 focused one, the NMR experiments, which includes the carbon-13 NMR and the DEPT, which is a distortionless enhancement by polarization transfer. And if you still cannot determine the structure after running the carbon-13, then you need to proceed with the 2D NMR experiments, which includes the proton-proton correlation spectroscopy and nuclear Oberhauser effect spectroscopy. Also, you need to use HSQC, which is heteronuclear single quantum coherence spectroscopy, and HMBC, which is heteronuclear multiple band coherence spectroscopy. So I will go through all of these NMR experiments later. So let's start with the carbon-13 NMR spectrum kasi most likely after running your proton, ito yung next na gagawin ninyo. So the carbon-13 NMR spectra looks like a proton NMR spectra except for the ppm scale. So for proton, usually it's 0 to 12, but for carbon-13, the ppm scale is larger. It's from 0 to around 200, sometimes 250 ppm. And we also still follow the same terms for shielded and the shielded region. The rightmost portion of the NMR spectra is the shielded region, and the leftmost is the shielded region. Also, the ppm scale starts at 0 on the right side, and as you go to the left, the ppm value will be higher. Now, the only difference with the carbon-13 and the proton is that in carbon-13, we do not use integration. We do not get the integral value of each signal kasi it's not really reliable for a normal carbon-13 NMR spectrum. But you can still have the chemical shift values, the number of signals, which represents the number of different types of protons and also their functionalities. So for this molecule, you have two different types of carbon, the CH3 and the carbonyl of the carboxylic acid. So you have two different signals here. Okay. Now, also similar with the proton NMR, you also have a carbon-13 chemical shift correlation table. So you can find this in any textbook or also in the internet. And you will notice na mas malaking spread niya is from 0 to around 250 ppm. And also, you can refer to this if you are not sure kung anong functionality ng chemical shift na nakikita niyo doon sa carbon-13 spectrum niya. For example, if you have a signal at around 22, 23 ppm, then most likely it's a saturated CH. So that's true for acetic acid. Now, sometimes carbon-13 is not enough to help you determine the structure. Halimbawa, hindi mo alam kung CH ba yun, CH2 or CH3, yung carbon na tinitignan mo sa carbon-13, then you can go to DEPT. So DEPT is the preferred procedure for determining the number of protons directly attached to a specific carbon-13 nucleus. So there are different types of DEPT experiments. You have the DEPT 45 degree, DEPT 90 degree, and the DEPT 135 degree. So each of these DEPT experiment will give you different types of signals depending on the carbon. Okay. So if you have a carbon that is a singlet, meaning walang hydrogen na naka-attach sa kanya, hindi siya magbibigay ng signal sa DEPT 45, 90, and 135. So magiging blank yung region niya doon. But if you have a carbon with one hydrogen attached to it, so you have a CH, it will be positive on a DEPT 45, DEPT 90, and DEPT 135. Now, if you have a CH2, the signal will be positive on DEPT 45, but it will not appear on DEPT 90, and it will be negative on the DEPT 135. If you have a CH3, it will be positive on DEPT 45, it will not appear on DEPT 90, and it will be positive on DEPT 135. Okay, so medyo mahirap tandaan yung mga signal patterns for each depth, pero ito yung pinakamadali. If you are using a depth 45, ang signal lang na lalabas doon are all positive, and they are signals come from carbons na merong naka-attach na hydrogen, whether it be 1, 2, or 3. So yun sa depth 45. For depth 90 naman, ang signal lang na makikita nyo is a signal coming from a carbon with one hydrogen attached to it. So CH lang. For depth 135 naman, you will get a signal from CH and CH3 that are positive and CH2 that is negative. So tingnan natin kung ano yung itsura nito dito. So for example, you have this molecule, and this is the standard carbon-13 spectra of this molecule. You'll notice that if you count the number of signals here, that will be equivalent to the number of carbons nitong molecule na to. So you have 1, 2, 3, 4, 5, 6. This is from a solvent, 7, 8, 9, 10. So you have 10 carbons for this molecule. So the next problem that you will encounter is, ano ba tong mga carbons na to? Sila ba ay CH3, CH2, or CH? So that's when the EPT will help you. So let's look at these three signals first. So if we look at the depth 135, you will get three signals that are positive. So meaning it can either be CH or a CH3. Okay? Kasi CH2 is negative in depth 135, such as this one. So hindi pa natin siya ma-distinguish kung CH ba siya or CH3. So you need the depth 90 because in depth 90, only the CH will appear. So if you look again at these three signals, nawala yung dalawa. Pagdating natin sa depth 90, ito na lang yung natira. So meaning, this signal coming from this carbon, it's a CH, and these signals are CH3 kasi hindi na sila lumabas sa depth. And if you look at the structure of the molecule, indeed we have two CH3s here, itong carbon 1 and carbon 9. So most likely these two carbon signals are coming from these two carbon. Okay, so that's how depth helps you interpret your carbon-13 NMR spectrum. Okay, so if you send a sample for carbon-13 and depth analysis, ito yung makita nyo. Again, there are no structures. What you will get is just spectra. And then you need to interpret all of the signals coming from this carbon-13 and this set of depth experiments. So napansin nyo, hindi lumabas yung mga carbons na to sa 45, depth 90, and depth 135. So meaning, they do not have any hydrogens attached to them. And also you can do the same interpretation for these types of carbon signals. So how do we interpret carbon-13 and depth? So this is a summarized workflow. So first you list the signals or the chemical shifts of all the non-equivalent signals. And then you determine the type or functionality of the carbon by checking chemical shift correlation tables. And then you identify the multiplicity of each carbon signal by referring to depth. So multiplicity meaning, is it a carbon with no hydrogen? Is it a CH, CH2, or CH3? So you can use the depth spectra. And then you create a table to summarize all the information. So if you follow that step, you will end up with a table that looks like this. So these are all the carbon-13 signals. And this is the carbon type coming from depth. So quaternary, meaning there are no hydrogens attached to the carbon. And these ones are CH, and this is a quaternary and the CH. And these are the functionalities that you can get by referring to chemical shift correlation table. So if you notice, iniwan namin blank yung region na to. Bakit? Kasi hindi kami sure kung anong functionality yung ilalagay dito. Kasi maraming carbon-13 signals that are overlapping on this chemical shift region. So hindi namin alam kung is it just an aromatic, oxygenated aromatic, or are they coming from olefinic carbons? So you can leave them blank when you are interpreting your carbon-13 and depth spectrum. Now, if your sample is known and you are already familiar with some of the common signals from known samples, if you look at proton and carbon-13, then you can just use the proton and carbon-13 to help you determine the structure of compounds. For example, you are just looking at known fatty acids, then you just use the proton and carbon-13. No need to do any other experiments. But if you get a novel compound, a new one that was not published before, and also if you get a compound with a very complex structure and you cannot use the proton and carbon-13 to build the structure of the molecule, then you need to use 2D NMR experiments. So what are 2D NMR experiments? So 2D stands for two-dimensional NMR, but this is a misnomer kasi a two-dimensional NMR is actually a three-dimensional data. So ito siya. So you have this X and Y dimension, and you also have the Z dimension for the signal. Now, bakit siya tinawag na 2D if three-dimensional data? That is because you are using two different frequency domains. So you have the F1 and the F2, depending on the type of 2D experiment that you are using. So in your 2D NMR spectra, you will not get this type of spectrum, but what you will get is this one. So this is your frequency 2 domain, and this is the frequency 1 domain. And then ito yung signal na ito. So if you notice, para siyang yung bundok na chinap mo into different layers, wherein this is the tip of the mountain. So ito yun. Then ito yung next layer, and then ito yung base. Okay? So ganun siya titignan. And if you interpret to the NMR spectrum, you always look at the center. Lagi kang dito titingnan. Okay? So there are two different categories for 2D. There are three distinct categories for 2D NMR depending on the nuclei involved. So you have the homonuclear, meaning the same nuclei are used. So these are the COSY and NOSY. And you also have heteronuclear, which means that you are using two different nuclei. So pwedeng proton and carbon-13, pwedeng proton and nitrogen, etc. So let's start first with COSI. So COSI in NMR in natural products is usually performed in order to build isolated spin systems or fragments of the molecular structure. So a COSI spectra contains a diagonal peak, which I will show later. And this is an information similar to a one-dimensional proton. And the COSI is symmetrical along the diagonal. And all other peaks that do not lie on the diagonal are called cross peaks. And cross peaks are the peaks of interest. So this is a typical COSI spectrum. So you'll notice that you have two frequency domains. So you have this spectra here, which has this ppm scale, and this spectra, which has this ppm scale. And this is the diagonal. Ito yun. Okay. So lahat ng signal coming from the diagonal is similar to the signal coming from the 1D proton NMR spectrum, meaning if you see a signal from this region, ito siya, sa proton NMR, and this signal from this diagonal is from this signal dito sa proton NMR, and the same is true for all other signals in the diagonal. So when we are interpreting the COSI spectrum, we do not use signals coming from diagonal, right? What we are interested with are all of the signals that are not on the diagonal. So it's sila. Ayan, these ones or this. So these are what we call the cross peaks. Okay. Also, another property of the COSI spectrum is that it is symmetrical along the diagonal. So meaning this side here is a mirror image of this region of your COSI spectrum. So ano ibig sabihin doon? So meaning if you have a signal from this part of your COSI sa upper side ng diagonal, then makakita ka ng signal na kaparehas niyan dito kasi it is a mirror image. Same is true for this. Ito yung mirror image niya. And ito naman yung mirror image niya. So when we are interpreting COSI spectrum, isang half lang ng spectrum yung kailangan mo. So ito lang, for example, or you can use this one, whichever you are comfortable with using. So ano yung ibig sabihin ng mga cross peaks na to? So let's take a look first at this cross peak for this proton 1. So this means that this proton here is neighboring to another proton signal that gives this cross peak. So if you look at this structure, this is proton 1, and isa lang yung katabi niyang proton, which is this proton attached to carbon 2. So ito yun. So meaning to say, this cross peak here must be a signal due to this coupling with this proton. So ito yun. So if proton 1 is this signal at 4.3, then proton 2 must be this signal at 3.2. So yan. Now you can extend this further. Pwede mong mahanap yung katabi ni proton 2, ito, which is this proton attached to carbon 3, by looking at the cross peaks ng proton 2. So if this is proton 2, ito yung next cross peak niya, ito. So makita mo na ito yung neighboring proton niya, which is the proton 3. Okay. So in COSI, you can build yung fragment by looking at the cross peaks, and you can also build the connection kasi makita mo yung mga katabi ng bawat proton. So if you continue interpreting the COSI by looking at the proton 3, makita mo pa yung ibang neighbor niya, which is this one. So you can say that, oh, it must be proton 4. And then yung iba pang cross peak ni proton 4, ito, this must be due to proton 5. So the way you build this is that it will never end unless the next atom do not have any hydrogen. For example, you have an oxygen here, walang na-attach na hydrogen sa kanya, or you have a carbon that do not have any hydrogen attached. So that is a quaternary. So dun lang mag-end yung chain nung fragment na nabubuo mo. Okay. So how do we interpret a COSI for natural products, for an unknown natural product isolate? So first, you need to prepare the proton NMR chemical shift kasi yun yung gagamitin mo na signals in interpreting the COSI spectrum. Then after that, for each proton signal list, you list all the COSI cross peaks on a matching row. So for example, you have this COSI NMR spectrum of an unknown isolate. So this is the diagonal, okay? This is proton spectra. This is a proton NMR spectrum. And these are the cross peaks. Ito, medyo maliliit lang. So what you will do is you have a table containing all of the proton chemical shifts. And then hahanapin mo kung meron bang cross peak yung proton na yon on the COSY NMR spectrum. For example, for proton at 12.483 ppm, so nandito yon, somewhere here, wala siyang ka-cross peak, so just leave it blank. Same is true for the proton at 9.396, so ito yon. So wala rin siyang cross peak, so just leave it blank. But once we go to 7.705, ito, you'll notice na meron kang cross peak dito, okay? So, meaning to say, meron siyang neighboring proton. So, you just write kung ano yung ppm ng signal giving off that cross peak for the proton at 7.705. So, 7.05 is this is the cross peak. So, ito yung proton na yan. Based on this table, it's at 7.55 ppm. So, you interpret all of the signals na merong cross peak yung proton na yun, and then you just build this table, because this will help you in building your structures later. So the next 2D NMR experiment that will help you build the structure is HSQC. And HSQC is a very powerful technique which can show you direct band correlation. For example, in natural products, we always look at proton carbon-13 HSQC. So it will show you, it will tell you which proton is banded to which carbon. Now, the most common use of this one in organic chemistry is proton and carbon-13, and it is a proton detected sequence. Now, compared to COSY, HSQC do not have any diagonal. So meaning all of the signals, all of the peaks on the 2D NMR spectra are cross peaks. So they are all peaks of interest. And the HSQC relies on JCH coupling. So meaning to say you need to be very careful if you have a terminal alkyne, because if you have this type of functionality in your molecule, makakita ka ng cross peak for this carbon and this proton, and this will give you a very wrong impression na isipin mo, yung hydrogen na to naka-attach sa carbon na to, which is not true, kasi it's attached to this carbon. So let's take a look at representative HSQC spectrum for this molecule here. So this is an HSQC spectrum. So it contains a proton NMR spectrum on the x-axis and a carbon-13 NMR spectrum on the y-axis, okay? And then it does not have any diagonal. So hindi to diagonal. These are all cross peaks. And since these spectrum do not have any diagonal, that means all of the signals are peaks of interest. Also, wala itong mirror image sa kabilang side kasi wala siyang diagonal. So kailangan mo interpret lahat ng signal na to. Okay, so now how do we interpret an HSQC spectrum? So first, let's take a look at this carbon here, carbon 1, which is attached to an OH and attached to one hydrogen. So since this carbon has one hydrogen attached to it, dapat makakita tayo ng HSQC cross peak representing this attachment. So based on this y-axis, ito si carbon 1, the very the shielded carbon at around 75 ppm. So if you look at the spectrum, you will notice that you will have this cross peak here. And this cross peak, if you look up dun sa proton NMR spectrum, you will see this signal. So meaning, the carbon giving this signal is attached to this proton giving this signal. Kaya siya merong cross peak sa HSQC. So this proton is this proton here. Okay? Now let's take a look at another carbon. Let's say we have carbon 3. So for carbon 3, this is ACH2. So meaning there are two hydrogens attached to this carbon. And if these two hydrogens are not equivalent, then you will see two different cross peaks for that CH2. So if you look at this carbon 3 here, you will notice that, oh, this could be one cross peak and this could be another. So meaning these are the two hydrogens attached to this carbon. Okay, so ito yun, and this one. So you can interpret all of the other cross peaks, and then you will build the carbon and proton attachment for this molecule. Okay. So ano yung workflow for HSQC interpretation for unknown natural products isolate? So of course, it's different kasi wala ka pang structure. You are still building the structure from the spectrum. So what you need to do first is you need to prepare the carbon-13 NMR chemical shift table for the compound kasi yun yung unang titignan. And of course, since you have the carbon-13, dapat meron kayong proton at hand kasi you need the proton chemical shifts. Now, for each proton signal, you need to list all the carbon-13 cross-peaks on a matching row. So for example, you have this unknown this unknown sample, and you have this HSQC NMR spectrum. So this is the proton spectra, and this is the carbon spectra, and these are the cross-peaks. Okay. So if we look at the whole spectra, we'll notice na ito lang yung merong cross-peak, so we can zoom in on this region. So ito siya. So what you will do is you will list all of the carbons and protons na merong cross-peak. So for example, for this compound, you have all of these protons here. And then by looking at the HSQC spectrum, the proton at 7.705, this one, has a cross-peak with this carbon at around 115.352. So you list it here. So meaning this proton is attached to this carbon at 115.352. And we can also use the signal at 6.190. So ito, this is 6.190. And if you look at the cross-peak, ito yung cross-peak niya. And this is cross-peak due to this carbon. So meaning this proton at 6.190 is directly bonded to this carbon at 98.453 ppm. Now, in HSQC spectroscopy, you need to be very careful with these types of cross-peaks. Ito. So if you notice, parang naka-attach siya sa iisang type lang ng carbon. But if you look at the carbon-13 spectrum for this HSQC, meron kang dalawang carbon that are very close to one another. So you need to be very careful in interpreting these types of correlation. Kasi baka magkamali ka. You might end up with this proton being attached to this carbon, hindi naman siya talaga totoo. So you will end up with a wrong structure. Okay. Now, what can we do with the COSI and HSQC data that we already gathered? We can use that to build fragments. So when we say fragments, that means they are just part of the molecule. So hindi pa siya yung buong molecule. Okay? So remember in COSI, you can you can build the fragment using neighboring protons. For example, this 7.705 proton is neighboring this or next to this 7.55 or 6.902. So you will see that in this aromatic ring region, if you have this 7.705, this proton is coupled to these two different types of proton via meta and ortho coupling, meta and para coupling. So you can build this type of structure. And if you look at this proton at 6.902, it is coupled to the proton at 7.55 and 7.705. So meaning it's either next to it or it has a J coupling with the other proton. So you can build that type of isolated spin system. And then after that, you can determine kung anong carbon yung naka-attach sa kanya by looking at HSQC. So for example, this proton at 6.902, ito yun. And if you look at the HSQC spectrum, you will notice that you have a cross-peak for this proton with this carbon at 115.869. So meaning they are directly bonded to one another. So you can also do that for this proton at 7.555 and 7.705, and you will build this fragment. You can build another fragment by using the proton at 6.415 and its correlation with the respective carbons. Right? So that's the fragment. Now, in a typical natural products structure elucidation, you will end up with so many fragments, such as for this one, LMOL. You might end up with this fragment here, starting from carbon 1, 2, 3, attached to 4 and 5. And then you also have this fragment and this fragment. So these bonds are just imaginary, the dashed ones. Now, bakit sila imaginary? Bakit hindi pa natin siya ma-attach itong carbon 5 with carbon 1 or this carbon 2 with carbon 3? That is because if you only have the HSQC and the COSI, mag-end ka lagi dito sa gantong fragments. Kasi ang carbon next to this one is quaternary, walang hydrogen. So there's no way to connect these two carbons using COSY. And also, you need to use other NMR techniques in order to build this type of carbon, this type of molecule na meron kang quaternary carbon. So what you need to do is you need to use HMBC. So HMBC is also a 2D technique, and it detects proton and carbon-13 correlation that are 2 to 4 bands away. So for HSQC, it's directly bonded, but for HMBC, it's 2 to 4 bands away correlation. Now, it's tuned to detect correlations by small couplings, and also similar to HSQC, there are no diagonals in an HMBC spectrum, and all cross peaks in the spectrum are peaks of interest. So this is a typical HMBC spectrum. So mapapansin niyo para siyang HSQC kasi the x-axis is a proton NMR spectrum and the y-axis is a carbon-13 NMR spectrum, right? Now, paano in-interpret ito? So these are all cross peaks, so they are all peaks of interest. There are no diagonals, and this side is not mirror image of this side kasi wala kang diagonal. So lahat ng peaks na to, you need to interpret them. Now, let's take a look at this proton. Itong proton attached to carbon 11. So ito sila, dalawa silang proton, 11 and 11 prime. Now, these protons are directly attached to carbon 11. So meaning it should not have any HMBC correlation with this carbon kasi it's direct attachment. Sa HSQC nyo siya makikita. But what you will see in HMBC is a correlation between these protons and this carbon because this is already 1, 2 bands away. Okay? So if you look at this HMBC spectrum, ito yung, let's take a look at proton 11. Ito siya. And if you look at the cross peaks, you will notice that you have a cross peak here and here. Okay? So for these ones, you get cross peak for carbon 2 and carbon 10. So carbon 2 and carbon 10 are 1, 2, 3 bands away. 1, 2, 3. So meaning they are 2 to 3 bands away from this proton. And since these two protons have the same environment, you notice that they have the same HMBC cross peaks. Okay? Now, saan importante yung HMBC? This is very important if you are trying to connect a quaternary carbon to your isolated spin system or to your fragments. For example, you want to connect this carbon here, carbon 17 with this fragment, the molecule mo. Then you need to find a correlation between the proton 16 and the carbon 17 and all of the carbons in this fragment that are 2 to 3 bands away from this proton 16. Okay? And also, if you have an OCH3, let's say this is not an OH, this is an OCH3, then the only way that you can connect an OCH3 to the structure is using HMBC. Okay? Now, the thing with HMBC is that there are times that the cross peak that you are expecting will not appear on the HMBC, and that is perfectly normal. Kasi hindi ganun ka-sensitive sa HMBC. But what you need to be very aware, particular of is yung HMBC correlation that should not be there. Kasi if you have, for example, this proton here, and meron kang HMBC correlation with this carbon at carbon 20, then ibig sabihin, merong mali doon sa structure na binubuo mo. Kasi hindi dapat yun mangyari. Okay? So maybe you misplace this proton, baka nandito siya, kaya meron siyang HMBC dito sa carbon 20. Right? So what's the workflow for interpreting HMBC for natural products? First, you prepare the carbon 13 chemical shift table, and then for each proton, you then list all of the carbon 13 cross peaks on a matching row, similar to that of HSQC. So you'll end up with this type of table. You have protons here, and ito lahat ng carbons that are HMBC correlated to that proton. So when you are interpreting this, ibig sabihin, this proton is 2 to 3 bands away from these carbons. Same is true for these other protons. Okay? So meaning to say, if you are trying to build this connection using HMBC, what you will end up should be a correlation between this proton of carbon 5 and this carbon, right? And also this proton and this carbon. Bakit? Kasi this proton is 2 bonds away from this carbon. So dapat meron silang HMBC correlation. And another one is this proton is 1, 2, 3 bonds away from this carbon. So dapat meron din siyang HMBC correlation. And the same is true for this proton kasi same lang din yung bond distance niya compared to this proton. Now, you can also do the same HMBC correlation with other protons ng fragment na to. For example, you have a proton here. Dapat meron siyang HMBC correlation with 1, 2, this carbon here, and also this carbon, and also this carbon. So you can build the fragment, right? So once you have interpreted of the HMBC spectrum, you can now safely connect all of the fragments, and you will end up with your structure, such as this one. This is LMR. Now, does it mean na tapos na ang ating elucidation? Now, it could be we can end up on an HMBC. However, there are times wherein you have carbons that are chiral. For example, this carbon here is chiral. And you need to determine the chirality of this carbon. So, hindi mo alam kung yung proton na to should be pointed away from you or pointed towards you. Same is true for this H3. Hindi mo alam kung pointed towards you or away from you pa siya. So, you need to do another NMR techniques in order to determine that. And also, if you are looking at journals, you will usually notice this type of notation. So you will see a structure na ganito, and then maraming arrow, and then maraming solid lines. So the solid line actually tells you that this carbon chain, this fragment, is built using COSY correlation. And then this CH3 is connected to this fragment using HMBC. So ganun siya in-interpret. Now, building this type of representation is an art. So hindi mo naman kailangan ilagay lahat ng HMBC correlation kasi magiging sobrang crowded na nung molecule mo. Puro arrows na lang yung makikita. So you just use the very important HMBC correlation. For example, hindi mo naman kailangan na ipakita yung HMBC correlation between this proton and this carbon kasi gawa mo na siya using COSY. So you just use those that are important. Okay. Now going back to the stereochemistry, we need to also prove this stereochemistry before we can propose this actual structure. And to do that, we need to perform NOSI, or what we call nuclear Overhauser effect spectroscopy. So NOSI is a true space correlation between proton nuclei that are close in space. So meaning hindi sila kailangan neighboring via band, but what they only need to be is they need to be close in space para magkaroon siya ng NOSI correlation. So this is very important in determining the relative stereochemistry of a compound. And just like COSY, meron tayong diagonal peaks sa NOSI spectrum. Diagonals are similar to the 1D NMR spectrum, and they are not peak of interest. But what we are interested with are the cross peaks. And since it has a diagonal, NOSI also is symmetrical along the diagonal. So this one is a typical NOSI spectrum. So for this spectra, you will notice that you have two colors. You have the black and the red cross peaks and signals. So the black is usually the diagonal siya. And all of the NOSI correlation are on a sign opposite that of the diagonal. So meaning if this black represents positive signals, then the red should represent red signal. And it means they are on the opposite signal of this diagonal. So ito yung mga NOSI correlation nyo. And if you notice, sobrang dami ng NOSI correlation dito. And if you try to interpret all of them, baka abutin ka ng months just to interpret them all. So ano lang yung kailangan natin interpret dito? Ang kailangan mo lang interpret diyan ay yung NOSI correlation that will tell you information on the stereochemistry of your molecule. For example, this carbon here. This carbon attached to proton Q is chiral. You have 4 different ligand groups that are attached to this carbon. So meaning it can either be the proton is pointing on the axial side of this chair conformation, or it could be on the equatorial. So you do not know. So the only way that you can prove that is by looking at the no-seq correlation noong proton na ito. So you have here this proton Q, ito siya. And if you look on the cross peaks present, meron siyang cross peak with these protons, this one. So ano dapat yung cross peaks na to, or ano dapat yung proton giving this cross peak in order for you to prove this kind of structure? So dapat meron siyang no-seq correlation with this proton, X, kasi they are close in space, para silang in axial position. And also, it should have a no-seq correlation with this proton P, because they are also both in axial, so they are close in space. Now, kapag nagkaroon ng no-seq correlation yung proton Q mo with the proton ng metal na to, that means mali yung stereochemical assignment mo. Dapat nandito siya pointing on this region, or maybe it should be directed to down, or either mali itong metal assignment mo dito. So, mean to say, you need to be very careful with interpreting no-seq, kasi mamaya you end up with structure that is wrong in terms of stereochemistry, because you cannot see the relevant no-seq correlations. Okay, so how do we interpret a no-seq for an unknown natural product isolate? So you prepare the proton NMR chemical shift table, just like in POSI, and then for each proton signal, list all the no-seq cross peaks on a matching row. This is the ideal case. But if you are short in time, what you need to do is just interpret the no-seq cross peaks that will tell you the correct stereochemical assignment. Okay? Now, now that you have an information on all of the NMR experiment that can give you the structure of the compound, how do you start your natural products journey? So first, you identify your target plant sample. So in identifying, laging tanongin yung sarili nyo, what makes the plant an interesting sample? Is it a newly discovered plant? Is it a plant that was not studied before? Is it a plant that has a very interesting biological activity? For example, kaya ba niyang cure yung cancer? Ginagamit ba siya in treating malaria or other diseases, etc.? Then you choose that plant. After that, you determine the effective extraction and isolation protocols. So for example, you already have the plant and you know its scientific name, so you know the plant's genus. You can check literature to determine ano ba yung compounds present on the plant's genus. For example, one of the plants that I work with are Hoya species, Hoya genus. So ano ba yung mga common compounds doon sa Hoya genus? So most of them contains triterpenes. So in-expect mo na ma-isolate mo sa plant na are triterpenes. So if the genus is well known to contain flavonoids, then you expect that the compounds that you will get are flavonoids, and you design your extraction protocol in order to get the flavonoid. Okay? Now, another question is, do you want to isolate the source of the plant's biological activity? If so, then you need to do bioassay guided extraction. So meaning, on each part of the extraction procedure, you need to test the extract whether you are still getting the fraction that shows good biological activity. Now, are the target compounds polar or non-polar? If the compound is non-polar, then you use non-polar solvents for extraction. If it's polar, use polar. Are you interested with alkaloids? Then if you are, use acid-base extraction to get alkaloids. Next is you prepare your isolates for NMR analysis. First is you ask yourself, is it already a pure isolate? So in order to prove that, you can use TLC, and if your isolate only shows one spot on your TLC, then most likely it is TLC pure. And also another question to ask is, can I get more than 10 milligrams of the pure isolate? If so, then proceed with the isolation para mas dumami pa yung pure isolate mo. Kasi the higher the mass that you get, the better the NMR spectra is. Then next question is, in what solvent is the isolate soluble? So dapat may idea ka nito. Because in performing NMR analysis, we will dissolve your isolate to a specific NMR solvent. So it can be deuterated chloroform, deuterated BMSO, deuterated water. So you need to know kung saang solvent siya soluble so we can use the appropriate NMR solvent. Now, these are some of the frequently asked questions when doing NMR analysis for natural products. So first, NMR analysis is so expensive. My funding is not enough. How can I make the analysis cheaper? So again, the length of the NMR experiment depends on the sample concentration. And if you can get higher mass of sample, then please get a higher mass and repeat the isolation kasi it will shorten the NMR runtime. Kasi kapag sobrang liit nung isolate mo, for example, you only have 1 milligram, then we might need 24 hours for a carbon-13 NMR analysis. Now, next, I cannot see anything on my isolate's NMR spectra except for solvent and water signals. What happened to my isolate? Now, hindi niyan ibig sabihin na nawawala yung isolate mo. Nandun pa rin siya sa NMR tube. However, the mass of the sample might be too low or the number of scans is not enough, kaya hindi lumalabas yung signal coming from your isolate. So we need to either increase the mass ng isolate or increase the number of scans doon sa NMR analysis. Now, why is the NMR spectra of my sample so dirty? Yun yung next na tanong. Now, in organic chemistry, in organic synthesis, we have this saying na garbage in, garbage out. So if you give us a sample that is very dirty, then you will get a very dirty NMR spectra. So sorry, your sample might not be pure. Right? So what you can do is you get the sample again and you perform further purification to get a better sample. Next, do I need all the 1D and 2D NMR experiments for my sample? This is a very common question for those that are starting in natural products. The answer is no, if the compound is common or is well known. For example, ang na-isolate mo lang naman is, for example, it's just a very common sterol such as stigmasterol. Then you just need proton NMR in order to determine its structure kasi pwede mo nang i-match yung proton NMR spectra niya with those found in literature. Now, if your sample is not known, you cannot find any match, then that is a good news kasi there is a chance that you are getting a new compound. So you need to perform 2D NMR experiments. Next, I don't know the solubility of my sample. Can I send it for analysis? Yes, you can send it, but we will play on your sample. We will use different solvent, and there's a possibility that it might degrade your sample. There's also a possibility that we will lose some of your sample during changing of solvent. So we recommend that you test the solubility of your sample first before sending it to us. And if you are doing natural products, then most likely may idea ka na kung saan siya soluble kasi you are doing TLC analysis. Now, in summary, these are all of the NMRs experiment that you can use, and we recommend you use them in this order when doing your structure elucidation for your natural products isolate. So first, we recommend you start with proton NMR spectroscopy because it will tell you whether your isolate is pure or not by just looking at the integral values. So if sobrang dumi, wag ka na mag-proceed sa carbon-13 kasi masasayang lang yung funding mo and you will not get in a good carbon-13 spectra. So what you can do is you can prepare hundreds of isolates or tens of isolate, and then you run all of the proton NMR analysis for those isolate, and then you just choose kung ano yung interesting and ano yung pure. And then you proceed with the carbon-13. Now, once you get a good carbon-13 NMR spectrum, you can do DEPT, 1490 and 135 if you need help on determining whether it's a quaternary carbon, CH2 or CH3. Now, if you notice that the carbon and the proton spectrum are very interesting, you haven't seen them in literature yet, then we suggest you proceed with HSQC and COSI so you can get an idea on the fragments. Then after that, you perform HMBC. So if your compound, if you can already build your compound by just using this and wala siyang chiral center, then you do not need to do NOC. You just end sa HMBC. But if it has a chiral center and you need to prove the stereochemistry of the chiral carbon, then we recommend you perform 2D NOC in order to build the actual structure. So that's it for today's talk. And if you have any questions, you can ask your question, or if you are very shy, you can email me at using this email at virgilio.ebajo@dlsu.ph. If you want to send samples to the NMR laboratory, or if you want to have a collaboration, you can send an email to nmrlab@dlsu.edu.ph. Okay. Thank you very much. I'm now returning the floor to our host, Karen.
Okay, thank you very much, Veer. Actually, and ko rin natutunan today. Thank you very much for that very comprehensive, informative session of presentation. And very approachable actually, di ba, Jeff? If you would agree with me also, parang very approachable kasi usually we get intimidated with NMR interpretation, di ba? So he has, Doc Beer has presented it to us very approachable. So thank you for that, Beer.
Ayan. So Karen, bibigyan muna natin siguro ng a few seconds si Sir Veer to drink water, no?
Yes.
So gagawin muna natin, we'll advertise siguro upcoming events of Filipino Science Hub. Teka, let me reshare my screen kasi I chose the wrong screen. Ayan. So Karen, let me know when you can already see my screen.
Not yet, Jeff.
Okay. Is it good now?
Yes, it's good now.
Oh, yan. Okay. So para po sa ating sa mga bago po sa ating bagong participants sa ating web events po. So we do this every Saturday po. So this is, I think, our 61st webinar sa Filipino Science Hub over the past year and a half. So asahan po ninyo na hindi po ito ang marami pa pong mga kasunod ito. So actually, sa December 4th po, we will be joined by Mr. Michael Arnante and he'll talk about multi-species cytogenetic analysis. So ito po yung 4th offering natin sa DLSU CIF and PhilSci Hub collaboration. So ito po ay next week na, di ba Karen? Next week na ito. And then December 11th po, this is our final webinar for this year. So we will have Dr. Mary Grace Garjan. She'll talk about the title of her talk is What's in Your Water? So an introduction to per and polyfluoroalkyl substances. So si Dr. Garja naman po is based here in the US. So asahan po ninyo yan. So yung December 18th and December 25 po natin, yung Saturdays na yon, wala muna po tayo, break muna po tayo, magbabakasyon muna po at magki-Christmas party ang taga Filipino Science Hub. And then January 15th po, the last and the final installment of the Salle University CIF and PhilSci Hub webinar series will be presented to you by our host for today, Dr. Ana Karen Lacerna, and she'll talk about liquid chromatography, so instrumentation and also its application in natural products research, right, Karen?
Yes. So see you again on January for that webinar. Ayan,
and actually po for next year, we're proud and we're glad to share that we will have themed months po. For example, April we will have a webinar series on everything biology. We'll also have one in chemistry, physics, agriculture, and a number of other allied science areas po. So marami po tayo niyan. So watch out for that. Mapupuno po ang inyong Saturdays ng 2022. All right. And after this po, at 1 p.m. in the Philippines, we will have the 8th episode of our podcast featuring our interns and young individual contributors. So this time around, we invited a speaker from UP Manila, and she'll talk about misinformation in relation to the COVID-19 pandemic. So watch out for that po at 1 p.m. All right. So si Sir Veer ba ay ready na for questions?
Yes.
Ayan. So actually, sir, we have a few questions, but then what I liked about your webinar is meron po kayong frequently asked questions na. So partly that will have already covered part of the Q&A. So we compiled some of the questions po from Zoom. So ito po, Karen and I will take turns in reading the questions po. So ito naman, so let me start. So this is from Eileen May Ang. So she asked, so good morning po. Thank you for holding the online webinars, which are very informative. So yung question po niya is not related to NMR, but you would like to ask for suggestions since you have been doing isolation of natural products. So how could they get rid of the salt from marine samples like sponges at the extraction stage?
Okay. So the thing with natural products, this is a disclaimer actually. Sobrang laki ng difference between terrestrial natural products and marine natural products. So talaga my answer may not be the correct one because we never dealt with marine samples. But I think there are extraction procedures such as using ethanolic extract in order to get rid of ionic samples, or you can also use ion exchange, I think, in order to get rid of salts from your marine samples. Those are just some of what I'm familiar of. Pero with the actual protocol, I'm sorry, but I'm not really an expert on marine samples.
All right.
If I may just add to that siguro, Veer and Jeff, no? So, yes, you can do desalting, like trying to remove the salts using liquid extraction. So you can, if you have a bit of an idea, if you're dealing with possibly ionic, pwede maging ions na compounds, and then you would have to adjust the pH of your extraction first, and then extract with, for example, ethyl acetate or DCM, chloroform, and from there, mahihiwalay mo na yung salts from your compounds of interest. And you can also consider making use of yung sinabi ni Veer, ion exchange, or solid phase extraction. So with solid phase extraction, you can remove out the salts as well, and then elute mo yung mga organic compounds with a suitable solvent.
Ayan. So, in layman's term po, marami kayo po pwedeng gamitin panghugas ng asin sa inyong samples. Yeah. And yeah. So, maraming salamat sa inputs, Karen and Sir Veer. Okay, on to the next question. Karen, would you like to ask this one?
Okay, so from Jason Alcano, interesting talk po, Dr. Ebajo. I am familiar with NMR po by theory, but not by practice. May I ask if yung compound annotation in an actual NMR experiment is automatic na po ba? Or kailangan pa po din yung manual paper and pen structural elucidation? What certain database po yung pwedeng gamitin for an NMR spectral matching?
Okay, this is a very good question. Now, if the sample is well known, then you can just do spectral matching. I will answer first yung spectral matching. Kasi there are already tons of databases. Karen is very aware of this kasi in metabolomic studies, you are using database. And if you are looking at larger molecule, I think Japan has the SDBS database. There are some NMR software vendors that are also selling databases for natural products. But the thing with natural products, although there are so many databases, is sobrang bilis din ng progress with the natural products research, and maraming bagong compounds na na-add every month if you look at journals. So if your sample is known, then you can use SDBS database or other database that you have in your software. Now, with regards to compound annotation, unfortunately, it's not automatic. You need to build the structure on your own, and you need to annotate on your own using manual pen and paper elucidation. Now, the software can help you, for example, compute the coupling constants. It can help you tabulate, but with the actual elucidation, there are some softwares that are offering automated elucidation, but most of them are still not that reliable. That's why kailangan talaga ng practice when interpreting NMR spectra.
Okay. So if I could also make a comment, no, para kumbaga for relatability lang ng mga undergraduate students sa Philippines. So ito po, just to give you an idea, so I specialized in organometallic chemistry in my PhD. So ang nangyari po doon, so like I had to take advanced organic chemistry and advanced spectroscopy courses rin, no. So pag and I studied in the University of Alberta in Canada. So when I took up my spectroscopy course, yung na-cover namin sa UP for 1 semester, natapos namin in 2 weeks. Kasi 'di ba yung traditional na yung 'di ba yung one dimensional like proton NMR and carbon 13 NMR, and then you practice it on paper, hindi mo naman nga siya nagagawa sa lab, hindi mo siya na-actualize. Pagdating po ng third week, when they introduce yung second order coupling, kung paano ka mag-assign, ano ba talaga multiplicity nun, and ano ba talaga yung structural implication ng, kasi diba sa atin pag maraming signals multiplet lang, multiplet, okay, multiplet, and then you imagine ano ba yung possibilities. Meron po kayong mga processing of those signals that you have to do na kailangang maturo rin sa inyo. So yung pinakita sa inyo ni Sir Veer, that should already give you an idea of the vast number of techniques within nuclear magnetic resonance spectroscopy. So this is giving you an idea kung ano ba talaga yung ginagamit sa actual complex structural elucidation. So you're lucky that nung ngayon alam niyo na merong 2D NMR, 'di ba? Merong correlations between carbons, may correlations between carbon and proton. So that's very important. Nung pumunta ako ng grad school, na-shock ako. Kasi nung third week, parang 2D NMR. So English naman yung pagkakaturo sa amin, pero parang Chinese yung dating sa akin. So, no kidding po. So, eto, yung sa mga undergrad students dyan, nakakaiyak to sa grad school. So ngayon alam nyo na, simulan nyo na siyang intindihin para hindi kayo masyashock. Yan, side comment lang yun, Sir Veer. Alright.
Yes, yes. Kaya yung discuss ko today is just the simple first order coupling ng multiplets.
Yan, opo.
Pero if you go to complex, yung mga DDD, double triplets, it takes two sessions.
And then try to understand your quantum chemistry, kasi kapag solid yung inyong quantum chemistry background, yung physics part ng NMR, mas madali niyo maiintindihan yung spins, yung mga ganong aspects niyan. So ayan, so thank you so much, Sir Veer, kasi I was really glad to see na pinakita mo yung mas modern takes on spectroscopy, hindi lang yung ating kumbaga one-dimensional plots. Anyways, ayun. So okay, so ang next question naman natin is from Miles Angelo Sodehana. So sabi niya, tanong ko lang po, what should we do if ever may overlap po sa proton signals during the analysis sa proton NMR? Tsaka ano rin po ba yung software na pwedeng gamitin to analyze the results?
Okay. First, doon sa overlap. So with regards to overlap, there are times that we can do something. There are times that we cannot do anything. So ano yung times na pwede tayong meron magawa? If you have overlaps on the aromatic region, what we can do is we can do benzene titration. So sa NMR tube mo, containing the sample and the solvent, for example, CDCl3, you can add small amount of deuterated benzene in such a way until the point na when you run the proton NMR spectrum, naghihiwa-hiwala yung aromatic signals mo. So that's what we call benzene titration. But that is not useful all the time. Meron times na as the signals move, nag-overlap naman siya sa kabilang region ng NMR spectrum mo. So hindi siya laging useful. Now, what are the times na wala tayong magagawa? For example, in the shielded region, yung mga aliphatic, mga CH3 na yan, CH2 na yan, sorry, wala talaga tayong magagawa. Kaya kapag nakakita kayo ng natural product sample na mayroong fatty acid, for example, sterols. So sterols, sobrang dami niyang CH2, CH3s, o overlap pa yung fatty acid. Wala na tayong way to remove the fatty acid from that. So what you can do is you can do better sa inyong isolation to remove the impurity. Aside from that, you need to be aware on what signals are common as impurity. So yan na yung water signal, nandiyan na yung signal ng solvent na pinangwawash sa NMR tube, yung ethanol, nandiyan din yung signal na residual solvent mo, yung mga ether, chloroform, And also the fatty acid in natural products. Lagi yung nandun. Fatty acid, chlorophyll. So you need to be aware. Para on your own, you can say that, oh, this signal is not part of the molecule. So maybe the integral coming from this signal is not just due to my sample, pero galing din siya sa impurity. Then what softwares can be used? Sobrang dami. The most common is Metronova, but it's not free and it's quite expensive. Other software that you can use is the Geol-based software, which is Delta. And it is free. You just need to register sa Geol database to get the free software. And others are the ACD labs have their own software. Bruker has their own top spin. Varian also has their own software. So those are just some of the softwares that you can use.
Ayan. Pero I actually sir, yan. Pero tip lang sa students, no? Ako, this is coming from someone who has actually practiced both the use of software and yung paper interpretation. It always helps na yung basics ay alam nyo kasi there will come a point na kapag sobrang nagdepende kayo sa software, malilimutan nyo na yung technique sa kung paano ba yung pag-deconvolute nung signals, no? Sa NMR niya. All right.
Agree ako dyan. Kasi ako, my applications are in metabolomics. So, super, based sa spectral matching. Which is, I think I can also add to what Beer has said in terms of software. You can make use of Kinomics, NMR. So, for human metabolites, they have the Kinomics software. For some cases, you will be able to distinguish, even though meron ka mga overlaps of signal, you can still profile the concentration of certain compounds as long as meron kang ibang signal na pwedeng pagbasihan ng concentration. Now, it will work in some cases kung meron pang ibang signals, pero kapag all of the signals are in an overlap region, mahirap na rin talaga siya. Wala ka na rin magagawa in terms of kinomics. So, yun for metabolomics and other small molecule applications for known compounds.
So, but also very important yung sinabi ni Sir Veer kanina that kailangan aware ka ano ba yung potential impurity sa sample mo.
Yes.
Yeah. Yes, Karen.
To add to that, minsan yung acetone na ginagamit for drying,
yeah.
Sasama rin yun. So, kailangan, yun, ensure nyo na dry din yung...
And for example, water, no? Yung proton exchange, no? So sometimes that proton can show up anywhere in the spectrum. Depende din yan sa solvent. So, essentially, lahat ng potential sources of, foreign signals, kailangan at least meron kayong idea saan ba posible mangyari yun. Kasi if you're not keeping track of potential impurities, then, yung kung ano man yung nakaka-overlap dun sa main signal nyo, it'll remain a mystery. So, ayan. Alright, next question naman, Karen.
Okay, so from Jason uli, could you share some common errors and pitfalls that we have to avoid in 1D and 2D NMR structure elucidation? Salamat po. Thanks po.
Okay, first in 1D. So 1D, there are cases that the student is very reliant sa chemical shift correlation table. There are times na yung signal mo, which should be, for example, an OH should be at around 3.5. Hindi siya lalabas sa 3.5. Minsan nasa 12 siya. And that is due to the structure of the molecule. So, common yan sa flavonoids kasi there's an intramolecular H bonding doon sa flavonoid and it shifts the chemical shift ng signals. So, how to avoid yun sa 1D? One thing is you need to be familiar with the common skeletons. Halimbawa sa flavonoids, may lumalabas agad na alcohol at 12. And in cycloartenyl type, yung cyclopropane ring, may lalabas kang proton at a very sheet-led region na 0.7 ppm. So yun yung common sa 1D. Now with 2D NMR, this one is more difficult kasi if you look at journals, sobrang daming structure na mali. Kino-correct sila kasi mali interpretation ng 2D. So ano-ano yung mga common sources nun? One is maling interpretation ng HMBC. Remember that HMBC bonds are 2 to 4 bonds away. So pwedeng yung 4-band, in-interpret nila as 2 bands away. So it's common. Also in NOSI, minsan hindi nag-appear yung NOSI correlation, so they assume this type of stereochemistry for that molecule. So yun yung common. Now, the way we correct this at present is sometimes they do computational methods to simulate the spectrum, isa yun. Another way is they use other techniques to confirm the structure. So pag meron kang crystal, you can use single crystal X-ray to confirm the structure. Another one is you can synthesize the compound. Yun talaga yung absolute. Parang synthesize, compare the spectra with the structure. Okay. So yun lang.
Ayun. So siguro in the interest of time, we can entertain one more question. No? So this question came from Miko de Guzman. So ang tanong po niya, so sir, would it be possible to use NMR for cancer cell related research?
Yes, oo. If you are dealing with interaction ng, for example, a certain protein doon sa cancer cell and another drug, there are a certain NMR experiment that can help you. So yun yung tinatawag na STD NMR, Saturation Transfer Difference NMR. And sobrang sikat niya ngayon sa COVID research kasi you have the COVID virus, and then alam mo yung enzyme ay yung proteins na present doon sa kanyang envelope, and you are testing anong compound yung mag-interact. So you can use saturation transfer difference. So what it does is you have the protein in an NMR tube, you have the sample, and then ang gagawin ng NMR, hahanapin niya anong compounds present sa yung NMR tube ang mag-interact doon sa protein. So there is a certain NMR technique for that. And also NOSI is helpful. NOSI yung pinaka-common for biological samples.
Okay, Vir, if you can also expound a bit more on, okay, so we know of the application of NMR for structural elucidation as well as for these drug interaction studies. Ano pa yung ibang pwedeng paggamitan ng NMR?
Okay, yung isa sa pinaka-common right now is yung metabolomic studies. Proton NMR and the 2D NMR techniques are very common. You can also do quantitative analysis. So napansin niyo puro qualitative ang ginagawa natin ngayon sa structure elucidation. But you can also quantify. So for example, you want to know the purity of a certain drug. Halimbawa, bumili kayo ng USP sample and then sabi niya 98% pure, but you need to prove na 98% pure siya. Then you can use quantitative NMR analysis. Now, there are also some other application in food naman. You can do quality control. So alam mo kung ano yung peking food products. This is very common for olive oil. Maraming pumipeke ng olive oil abroad. So you can use NMR and check the fingerprints ng olive oil and the very common ina-add sa olive oil na pameke. Also in honey yung isa pang very common na food na pinipeke by adding sucrose, corn syrup, ganun, para mas mura. So you can detect that using NMR. So sobrang dami. What I just represented you is a portion of what NMR can do, and it's just in the field of organic chemistry. Marami pa siyang kayang gawin, lalo na sa analytical side.
At saka yung mga kinetic studies, no? Pwede rin siyang gamitin for those.
Kinetic studies, the terminal plate, yes.
Actually, NMR is a very powerful technique. And yeah, so Sir Vir, siguro can we ask siguro for a message of encouragement lang sa mga lalo na sa mga undergraduate students, no, na babago nilang natututunan yung NMR, baka po pwede niyo silang ma-encourage not to get intimidated by it.
Yes. So lalo na sa mga STEM student, this is very common na when you go to research contest, they always have natural product studies, for example, anti-cancer, anti-malaria, antifungal, that ends in crude extract, ethanolic extract, methanolic extract, etc. Now, I want you to start from that and then to go further. Kasi what if you found a plant that has a very, very high activity and maybe it is the next blockbuster drug? Then I suggest that you proceed with the isolation of the compound na causing that activity. Kasi at present, in Philippines, we now have all of these instruments that can help you determine the structure. You are very lucky. Because in our time, ipapadala pa namin yan sa abroad, mag-aantay pa kami ng 5 months para bumalik yung spectra. Tapos malaman namin yung sample namin hindi pure, ibabalik sa amin yung sample, purify ulit. Ng mga 3 months, papadala ulit, 1 year, etc. Now you are lucky. The instruments are here in Philippines. So the only thing missing are the researchers. So do not be intimidated sa mga information na makuha niyo from the analysis kasi we are here to help you interpret all perspective.
I think that's a very important. So a couple of very important things to emphasize. No, we do have local facilities in the Philippines like DLSU CIF, and Sir Veer already, so you can contact him. And then secondly, don't get intimidated. So even if you don't know how to conduct NMR experiments or even interpret yung data ninyo, there are experts who can help. So yun lang yung gusto naming i-share din sa inyo. So ayan, so this has been like a very great session. So like, by the way, we had about 170 participants today who stayed on for the entire session. So congratulations, Sir Veer and DLSU CIF. This has been like a very well attended webinar series. And so by the way po, we have already shared the link para po sa ating Google form for you to get your participation certificate. So just like a couple of reminders lang po. So the certificate of attendance, it's actually generated automatically. So automated yung system namin. So give it some time po. Sometimes it takes 7 to 10 days before namin ma-complete lahat. So please bear with us. And then secondly, pag fill out niyo po yung Google form, make sure that you type in the right information. Kasi kapag mali po yung spelling, mali yung mali yung inyong email addresses, yun lang din po yung isi-spit out ng system. So paki-check na lang po nun. And then ayun, so maraming salamat po uli sa pagsama na naman ninyo sa amin sa isang Sabado. Gaya po ng sinabi namin, next week naman, multi-species cytogenetic analysis by Mr. Michael Arnante. Ayan. So magkakasunod po tayo. And again, we would like to thank the Salle University's CIF for this for generously sharing their expertise and time with us. Hindi po sila nagpapabayad at nagbabahagi po sila ng kanilang serbisyo at ng kanilang kaalaman para po sa ating mga estudyante at sa ating mga guro. Maraming salamat po uli sa inyo. Ayun. Ayan. So yun, kita-kits po ulit tayo sa Sabado. And then Karen, Sir Veer, meron po tayong very quick debriefing session lang po in a separate Zoom session. So para po sa inyo, yun po, just paki-take note na po ng link para dun sa Google form kasi po we will soon end this session. So again, maraming salamat po sa inyong lahat.
Yun. Thank you everyone. Thank you, Veer. Have a great weekend. Enjoy the rest of the weekend.
Yeah. Karen, I'll send you the Zoom link. Paki-forward na lang kay Sir Veer. Alright?
Okay.
Maraming salamat po sa lahat. Ingat po kayo.
Thank you very much, everyone.
Bye.
Thank you.